from 2 raised to the power 0 to what? 2 raised to the power 7. So 0, 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 3, and so on and so forth. So I'm going to input my as logo FD, which is the flow direction. This is the cell individual. That means the cell on column 2, row 2, column 2, row 2, which is the cell on column 2, row 2, can flow in 8 different directions. Can flow in 8 different directions. Just as name implies, D8, 8 different R2 box. Then under our R2 box, special analyst 2, under special analyst 2, hydrology. Under hydrology, we click on this and we'll see our flow direction 2. Flow direction 2. You can also see that flow direction 2. So we click on that. So after we click on that, we input our surface raster, which is our field, our logo field. That means the data we got after we carry out our field analysis. So we click on that. Then we have our output. Our output is logo flow D. That's flow direction. So like I said earlier, you are going to use the D8 algorithm, which is a 3x3, uses 3x3 cell matrix to calculate the direction of flow of the innermost cell outside of it. So now it's telling us that the innermost cell can flow in 8 different directions. Outside of it can flow outside in 8 different directions. And like I said, the flow is in a binary format. It's in a binary format from 2 raised to the power 0 to 2 raised to the power 7, 8 different directions. So, and any 3 raised to the power 0 is what? 1. So, one is the flow direction in the eastern direction. The eastern direction, the cell that is directly east of our innermost cell. So that is our cell 1. That is the cell with value 1, which implies the eastward flow from the middle cell. Eastward flow from the middle cell. And this D8 algorithm goes in a clockwise direction. So after the eastward flow, we have what? The southeastward flow. The southeastward flow, which is 2 raised to the power 1, which is 2. Then we have the southward flow, which is 4, which is 2 raised to the power 2. Then we have the southwestern flow, which is 2 raised to the power 3, which is 8. Then the western flow, which is 2 raised to the power 4, 16. The northwestern flow, 2 raised to the power 5, 32. The northern flow, 2 raised to the power 6, 64. And finally, the northeastern flow, which is 2 raised to the power 7, 128. Beautiful. So after I run this analysis, we'll be able to have a mental picture of what I just explained now using the D8 algorithm. I believe we are all following up to this extent.
Yes.
So wait for it to so we can see, like I said earlier, the D8 algorithm has what? 8 different directions. 1, 2, 4, 8, 16, 32, 64, 128. Like I said, a binary format in the power of from 0 to raised to the power 0 to what? 2 raised to the power 7, which is 1 to 128. 1 here simplifies what? Our eastward flow. 1 simplifies our eastward flow, and forward 2 represents what? Our, if you can see this place very well, you notice that this falls in our southwestern direction. This particular place where my cursor is. I believe you can all see that.
Yeah.
While this red represents what? Our southern flow. This 4 represents our southern flow. The image is a bit coarse because of the number of possible flow direction of flow within our study area. But I believe from our own explanation, we can be able to understand all the different flow direction of flow that can possibly occur using our elevation data. So I won't dwell much on this. Also after the entire process, we can also ask our questions for areas that is unclear to us. So after we do the flow direction, the next thing we are going to be doing is what I call the flow accumulation analysis. To do the flow accumulation analysis, we would go through our toolbox, spatial analysis, hydrology, and what the flow accumulation. So for the flow accumulation, there are two. The most important parameter is what the flow direction raster. So the flow accumulation just shows us the areas that have high accumulation or high possible high accumulation of water within the study area based on the direction of flow. You know, once water flow in a particular direction, the accumulation, the area with higher flow with more flow direction has a higher probability of having a higher flow accumulation as compared to areas with just little flow direction or direction of flow, as the case may be. So output accumulation data got my flow, my logo flow ACC flow arc. So I will input this. I will um run my data my tool and check out for results. So wait while that loads. Okay, beautiful. So while this itself is the because the region highlighted as black have its own flow accumulation, but because of the little the little flow accumulation present in this area, it is shown as black. While we can see that this region highlighted as white, from this our data value, you can see that the region highlighted as white has a higher flow accumulation, and you can see that this is draining directly to this, while this other tributary is draining directly to this. So that means that the area highlighted as black has the lower one, while the area highlighted as white has a higher flow accumulation. But this is not the end result. Now we want to um and make our data, our flow accumulation to be a bit more detailed, to show us the other tributaries that are contained within the flow accumulation in middle, but I can't see now. So that brings us to our next analysis, which are going to be doing using the raster calculator tool. So I'm going to be using the search tool here to get my raster calculator. What I'm just going to do is what? Input my raster calculator. Now, the mathematical operation we're going to be performing on this flow accumulation is uh, logarithmic mathematical mathematical operation. So we are going to convert this from pixel values of 5,447 to logarithmic value. So like I said, my raster calculator, I'm going to be using what? Under this, you see, these are the operator keys, and mm, these are the different operations, mathematical operations that we can carry out. So I'm going to go to my log base 10. Also, let me just refresh our mathematical knowledge. You know, log 10 of 10 raised to power 1 is 1. Log 10 of 10 raised to power 3 is what? 3. That means log 10 of 1000 is 3. That means 10 raised to power 3. Log 10 of 10 of anything is what? 1. That's 3 times 1, 3. So log 10 of 10 raised to power 4 is what? 4. Log 10 of 10 raised to power 5 is what? 5. So I'll drag this I left click on this and drag this uh into this bracket here. That's what the log 10 of our logo flow arc. So I'm going to specify my output to be what? Log logo log 10. So wait for our analysis tool to run so we can see the. Okay. Okay, we can all see, you can see this. Can we all, I believe we can all see this. This is quite more detailed than the one we had. I'm just going to uncheck all these other all these other data so that you can as well see. Wow, this is so so class, so class, so class. Okay, all right. So there I have my data, and you can see the different tributaries. But this is not the final analysis. What we're going to be doing is, since we are going to be telling our computer that the values we have is too coarse, is too much, and would want it to exclude some values. We want to exclude some values so that the data so that it can improve the readability of our data, and also give our analysis a more intriguing result. So I'm still going to use my raster calculator, but this time I'll be using doing the telling the computer to do passing a conditional statement that, okay, if it satisfies this condition, run. If you satisfy this condition, run. So for my master raster calculator, I'm going to use this contour, the contour. So I click my contour. You should know that our contour has um a bracket, two parentheses, and a comma separating it. So the first thing we are going to do is what? Bring in our log 10 data that we've already calculated from our full accumulation. We bring it in, then we use our greater than or equal to operator. Greater than or equal to operator. Then I'm going to be selecting, for the sake of this analysis, I'm going to be selecting a value of 2. Then after that, we'll now bring in this again. So what this is telling our calculator to do is that for every value greater than, that it should only show us values that are greater than or equals to 2. That means values that are lesser than 2 and below should be ignored. That is basically what the conditional tool is telling our raster calculator, that okay, I just want to show me values that are between 2 and greater than 2. Don't show me values that are between 0 and 1.999. So like you said, we save it again. Logo, this time around we will be using I personally will save it as uh, con, for the sake of analysis, so that we don't get mixed up. Okay, so this is our this is our resulting data. These are resulting data. I'm going to change the symbology so that you can all see the stream network and how awesome it looks. using a different color right now. So let me just select this blue so you can see it. So I believe you can all see this. So basically here, the region with higher flow accumulation is highlighted in this deep blue. Let me just zoom in so that you can see what I'm talking about. It's highlighted in this deep blue, while the other ones that have a smaller flow accumulation is highlighted in this light blue, like I as shown in our symbology. So this in itself is not the final result. This just shows us, the various stream networks that are within our able to get the final result. We are going to do another analysis. This one is what the stream order analysis. Basically, what the stream order analysis is, what it orders our stream segment based on uh, uh, the different classes identified using the Strahler technique. What is the Strahler method of classification? It shows that two smaller is just two smaller segments meet to form a bigger stream segment. That a stream order of a river of stream order one and stream order two must converge to form a stream of stream order two. When I do the analysis, you know this better. So I'm going to input my stream master to be my logo con, and also input our flow direction master, which is our logo flow D, which is flow direction. So just the stream order, let me just quickly do that. Logo stream order, logo SO stream order. So using our method of streaming order, Strahler technique. Remember Strahler technique. Okay, right. We are on track.
Okay.
Uh, I apologize for this time consumption, but I just want us to have grab the nitty-gritty of the entire analysis.
It's fine. It's actually very important. And I think for those other team members that are watching this video, they will find it more interesting. So it's the best. It's not just this night alone. To serve as something that everybody can always look back to whenever they start
Yes,
working.
sir.
So thanks so
Yes,
much.
sir.
Can go ahead.
Yes, sir. It's a privilege, sir. Thank you, sir. I'm grateful, sir.
Mm,
So, like I explained earlier, I told you the Strahler stream order technique or classification stream order classification says that when two lower stream order, that means a stream segment of stream order one and segment and another of stream order one connect, they form a stream order a stream of a stream segment having a stream order two. So as you can see here, this is one lower stream order one, lower stream order two converging to form a stream order what? Two. Can we all see a stream order two? So also we can also notice that stream order two and stream order two converge to what? Form a stream order three. Form a stream order three. In some very rare cases, we can also have stream order one this is what the Strahler order technique or lower stream order converge to form a higher stream order. So we can also see from our class, stream order one is highlighted in on this pale gray to form a stream order three, the particular place. Now, yes, beautiful. As you can see, the stream order three and another stream order three what come together to form what our stream order four. So for this particular analysis, we have four different stream orders. One, two, three, and four. 4. Beautiful. So the last analysis that we're going to be doing to carry out to give us our final stream feature is our stream to feature analysis. This stream to feature analysis basically converts our data from the raster format into what the feature format, which is our or polyline format, and this is done to enable us perform further analysis like buffering technique on our data. So I'm going to open this tool, this stream to feature tool. Remember our process, R2 box, spatial analysis tool, hydrology, stream to feature. So I will right double click on this. So I'll input my stream master. If you've been following, my stream master will be my logo stream order now. Logo stream order, which is the stream order classification based on the Strahler technique. Also, I'm going to use my flow direction, which is my logo flow D. So I'm going to save my output as logo stream. So we run it and we wait for the results. Okay, beautiful. So I'm going to uncheck this so you can see line features. So this is our polyline feature of just classified stream order. So we can check the attribute table to see the different number of features and also to know the number. So in this particular story area, based on my analysis, I have 802 different stream segments that are interconnected using what uh, the contour like I did and also the stream order. So 802 different stream segments, individual stream segments. Also from the grid code, this grid code is just from the grid code. You can just check the statistics. This grid code is our stream order, as done carried out by using uh, our Strahler method of stream of river ordering. So you can see the minimum value is what 1, while the maximum value is 2. Do you understand? I believe you are all following. And the number of stream segments is what 802. 802. So the sum and also the mean of our data. So I'm going to close this now. We can also see the distribution. One is the most is the frequency distribution. One has the highest number. That means one has over 400 different stream segments, while 4 is the least, having just below 50 stream segments. You can see the distribution just like that: 1 to 2 to 3 and to 4 and so on. So I'm going to close this and also close my table. So the next thing I'm going to do is now that I have my local stream and also my big river, the next analysis I'm going to do is the buffer analysis. The buffer analysis, for my buffer analysis, we are going to be using a particular radius for analysis based on the flood risk knowledge that we have. We For this analysis, we are going to be using a buffer extent of 2 kilometers for our big river river. This will tell us that regions that are within 2 kilometer radius of our big river are susceptible to flooding. And also this conclusion is based on one, our inferential knowledge, and also based on several literatures that have been carried out in the past to do what our flood risk mapping. Several literatures have noted that when a particular flooding event occurs and for areas that are very close to large area bodies like River Benue, River Niger, and some other big rivers. People properties within 2 kilometer region have high susceptibility to flooding as compared to regions that are situated farther from the river body, like 2 point something kilometers and above. So for this analysis, I'm going to be using what? My buffer two. My buffer two. So what I'm just going to do is, like I did earlier, I'm going to use my buffer, my search tool to figure out my buffer analysis. Also, um if you don't do the search tool, how can I if okay, now you might ask, if I don't do the search tool, how can I navigate to my buffer tool? Now it is simple. Don't panic. What I'm just going to do is what? My click on my arc toolbox. From my arc toolbox, I'm going to go to, so let me just, I can't see this properly. Um okay, not distance, not distance. Oh Lord God. Uh okay. Proximity to proximity to special it's not our specialist. Forgive me. It's like I've mixed it up. Class to what? Logo big river buffer. So this distance is very important. Value of field. So for this particular analysis, I'm going to be using linear unit, which is value. So I'm going to change this to kilometers. Since we already said that our analysis, that regions that are within a 2 kilometer radius of the big river buffer are more susceptible to flooding. So I'm going to come down, select my buffer type. For this particular analysis, I'm going to use full, then round. Also, click on dissolve. Right, I'll click on all. I will tell you how I'll click on dissolve in the next analysis. Why I chose dissolve. Why I click to choose all for my dissolve in the next analysis. So I just let this run and we'll see the results. Let me just quickly round up this session. We have 6 minutes to go. Um, 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 I believe we all got it to this extent. Yes. Okay, so this is the result of my buffer. Don't let me just show you the big river that I used for the classification all the time so that you don't get confused. Big river, big river, big river, big river. Okay, yeah, it is. So we'll drag this right up. So you can see the big river. This is the big river. So once if you just oh, so you can see that regions that are in this area have are more susceptible to flooding. So the next buffer is going to be my smaller stream. Remember that I already did the raster to polygon of my logo stream. So I'm going to be using the polyline features, raster to polyline, the polyline features, which is the logo stream for this analysis. So my how tutorial class was my logo stream buffer. So for this particular time, the analysis we deduced that based on several literatures, past literatures, and also our information knowledge, regions that are within 500 meters of this smaller segment are highly susceptible to flooding. So you are using 500 meters. So click on the buffer the dissolve type. Remember I told you that the dissolve earlier. Why would it be needed? This dissolve, why we are doing dissolve is so that um buffer that are overlapping each other will be jointed by the buffer tool. See, to specify that okay, the dissolve to be performed to remove the buffer overlap. This is just to remove the buffer overlap to ensure that everything key into each other. So the dissolve field, I'm not going to be selecting anything. Just leave it as it is and wait for our result to come out. Okay. Okay, this is the result of my buffer. So we can see how dense this is. So if I bring this in, we would have a clear picture. So this is our stream segment and also we have parameter buffer that we just did. So let me just select this and uncheck this so that we can have a clear picture. So the last second to last analysis is what our classification. So basically this is what we are going to be doing in the next a segment of this analysis. But when we can do the reclassification, basically what is the reclassification? The reclassification is just an assignment of values based on user defined values. Now you are telling the computer that for my particular flood risk map, I want you to assign a value of within the class of maybe 1 to 3, where 1 represents low risk, low flood risk, to high flood risk, or in a case 3 might represent low flood risk while 1 may represent high flood risk, dependent on the user defined values. Like I said, user defined values. So for this my analysis, the classification I'm going to be doing is a class of 1 to 5. But because of the peculiarity of the classification tool, we must ensure that all our input features must be in a raster format for the computer to be able to reclassify the values. So what I'm going to do is this: I'm going to convert my big river buffer and my logo stream buffer into what? Into raster. So how do I do that? What I'm just going to do is I click on my polygon. Remember my buffer is in polygon to raster. So I input that in my search tool and I click on polygon to raster conversion. Ensure that it's polygon to raster conversion that is clicked here on here. Don't click on raster to polygon so you don't have mistakes. Oh wow, less than 1 minute. Oh baraba. Let's be fast with that. So big river buffer. So click on that again. While that is loading. So click on polygon to raster again. This time small lower extreme buffer. Oh, I didn't specify the output feature. I didn't specify it. Okay, so let me just specify this so that you know.
We cannot hear you. Please unmute yourself.
Yes. So from the analysis I did, this after I did the polygon to raster um, conversion. So this is what I got. My Let me uncheck this so you can see. So this is the black is uh the polygon to raster buffer of my big river body, while the stream to STBF to raster is the polygon to raster of my smaller stream segments as seen here. So this is the second to the final phase. So the final phase is, like I said earlier, is the reclassification method technique. So what we are doing is we are going to reclassify our data based on the uh, reclassification, the user defined reclassification values. Like I said, we're going to be using a reclassification value of 1 to 5, 1 to 5, where 1 signifies the lowest and 5 signifies the highest flood risk vulnerability. So what I'm going to do now is I'm going to reclassify each of my criteria. If you follow this analysis very well, we note that we have 6 criteria now. We have elevation, we have the slope, we have the land to land cover, we have the rainfall, we have the distance to water to big river body, which is our big river buffer, and the distance to smaller river, which is our stream stream buffer. So the next thing we are going to do is uh, go to for our active box. From our active box, we select our spatial analyst toolbox. From our spatial analyst toolbox, we select our spatial analyst tool. Then from that, we go to reclassify tool. Reclassify tool. If you follow spatial analyst toolbox, spatial analyst toolbox, spatial analyst from our spatial analyst act toolbox, we go to spatial analyst toolbox. From spatial analyst toolbox, we go to reclass toolbox. Then from reclass toolbox, we go to reclassify. So we double click on reclassify. So we reclassify each value, each criteria. So the first reclassification I'm going to be doing is the logo DEM, which is my elevation data. So for our analysis, you have to be very careful now. Now, for my own particular analysis, 5 represent the highest risk flood vulnerability, while 1 represent the lowest risk flood vulnerability based on my own analysis. So what I am going to do is I'm going to classify these values based on that. So 5 elevation with having a places having elevation value of 55 to 11, we have 5, which is the highest. For a flooding event, flooding water percolates in area of lower elevation and area of higher elevation. That means water flows from region of what higher elevation to region of lower elevation. That shows that it shows the possibility of water accumulating in this region of low elevation, since water flows from higher ground to lower ground. So same goes for this analysis. Since I know that water is flowing from higher ground to lower ground, I want to place more importance on regions that have lower ground, that have lower elevation. So and like I said, my value is what for I is 5, while for low is 1. So I'm just going to reverse new values. So giving 53 to 11, 1 and 11 5, and this one 1. So I'll do that. And I will save it as a class elif 1. I've done before. So let that run. this is my classified data. One for high elevation and 5 for lower elevation. So let me just uncheck this. So I'm going to do the same analysis to classify for my slope. The same thing goes for slope. So I might not repeat this. The same thing goes for slope. Slope, higher slope, uh, a value of 1, while places with lower slope values have a value of 5. Just using our elevation technique. So once we close this, once I close, let me just close this so that I can show you the result. So once we do that, this is going to be the result of our slope. This is going to be the result of our slope, our classified slope. So you can see 1 higher places with higher slope values, while 5 has places with, if you zoom in very well, places with lower slope values. So we've done the class, the slope, the elevation, the slope. Now we are going to the land use land cover. For the land use land cover, we are going to be classifying it. Since we have only 3 land use classes, we are going to classify it based on 3 different values. We have 5, 4, and 3. So let me show you what I mean. Let me the 2 is here. Okay, we classify 2. Now remember that our land use land cover that we did, let me show you the land use land cover that we did. We have 3 different values, and while I was doing the reclassification at 16 and 1 and 24, remember that uh from our attribute table I imputed what each class is. 1 is what river body, 6 is what built up bare land, and 24 is what vegetation. Now for analysis, we want to prioritize the river body class because this is the most important class when it comes to flood risk, because flood itself is what water. So area where they have river body would give it a flood risk value of 5, while built up is the second in consideration, because built up, these are regions that are mostly affected by flood. Built up regions are mostly affected by flood because of what the different factors, such as the kind of drainage pattern they have, because of the compact surface and the likes. While vegetation is the least affected, because areas that are densely vegetated have high infiltration rate because of, one, the canopy cover of the vegetation, and secondly because of the surrounding environment of the vegetation surface. The Since the water is being trapped by the vegetation cover, when it reaches the surface, it does not have enough capacity to run off, so it just infiltrates into the ground in most cases. So like I said, I'm going to be assigning values to this one randomly. So 5, remember, built up bare land, 4, and vegetation 3. So class land use land cover. So we class our slope, elevation, land use land cover. So the rest is So this is the reclassified land use land cover. I just did now. So like I said, 3 vegetation, 4 built up, and 5 you zoom in very well, the river body. So that's good. So the next is my rainfall. So I'm going to reclassify the rainfall based on my rainfall distribution like I did here. So what? Go to your art toolbox, go to spatial analysis toolbox, reclass toolbox, reclassify tool. So for my analysis, like I said, I'm going to be classifying what? My rainfall distribution. I already have a number of classes. So areas with higher rainfall distribution of 147 to 148, 1487, 1474 to 1487 have a value of 5, while that of 1440 to 1448 has a value of 2. I'm going to class range. So wait for that. So this is the result of our classification based on that. So this is 5, while this is 1. So the next is, why do I keep closing this now? I'm going to reclassify our wow, these are 2 classes. Let me quickly change this classify to just 1 class. I made a mistake here, so just 1 class. Okay, so we have just 1 class. So we classify, like I said, add toolbox, special analyst, we class toolbox, then we classify. So we need to, so since you have us over, we have to be very careful here. Since our river polygon to raster buffer, our big river buffer is of high consideration. That means regions that are within 2 kilometers to the particular big river are highly considered regions for our flood risk mapping. So we're going to change the value to 5. Remember that 1 signifies low while 5 signifies high. So
Okay.
just change that. Hello, sir.
Okay. Yes. Following.
Class. So now that we are done with that, okay, this is our result. This purple, you can see fly 5. This is our classified value. So we repeat the same process for this time, which is our last class, last but not the least, the stream feature that we just did, stream to buffer feature raster. Remember that for us to be able to reclassify, we must convert our data from polyline to polygon. So the same thing applies for here too. Since you are given a concentration of 500 meters to areas that are within a particular river channel or stream channel, we are going to use the same value of 5 to denote that regions that are within this area are highly susceptible to risk to flooding. So so we do the same. Wow. Why is it showing two windows? Arcmap, why is it showing two different windows? What is this? What's what is my app? Right. So after you have all our classes, after you have all our classes, um, okay, just if you can just group everything, so that when you're doing your classification, you don't have to be, select everything and move it. So for our weighted overlay, how we're going to, I think it's use. So so after you have your class values, what you're just going to check the elevation to what to do the weighted value. You go to Arc toolbox. From your Arc toolbox, you go to the overlay tool, to the special analyst toolbox. From the special analyst toolbox, go to the overlay toolbox. From the overlay toolbox, you see your weighted overlay tool. Like I said, Arc toolbox, special analyst toolbox, overlay toolbox under the special analyst toolbox. Then you see your weighted overlay. So this is where I'm going to round up today's session. We will continue the session in another class. Thank you everyone for being a part of this. Uh, Thank you for the opportunity, sir, to be able to anchor this section.
Yes.
Yes.